So in the lectures, we introduced this idea of projectile motion, and what we pointed out is that in this projectile motion, we have a particle describing this parabolic path. Okay, so we have the particle is launched with some initial velocity v naught at an angle of theta to the horizontal direction, and because we have an acceleration which is acting downwards, which is this minus g. In fact, as I've drawn the angle downwards there, I could just write g. The particle moves horizontally exactly as it would as if it was just if we'd launched it horizontally, but the vertical motion is affected by this acceleration. So we're always accelerating downwards, so the upward velocity component is decreasing until we reach this apex, and then we come back down to Earth. And I mentioned in the lectures that we have this key concept, which is the range of this motion. And if we look at the equations that we set out in the lecture. So we know from the Suvat equations we have this S equals ut plus a half at squared. And if we consider this in the vertical direction, so in the vertical direction we have, well, S, we start basically here and end here. So the displacement is zero because we start and end at ground level. So the displacement is zero. And then we can write the right-hand side of this, we can have t, there's a common factor t here. Our initial velocity is going to be v naught sine theta, okay, because that's the component of the velocity acting in the vertical direction here, so v naught sine theta. So that's u plus a half at. So we're going to get plus a half minus g, so let's actually rewrite that as v sine theta minus a half g t. So this is a quadratic equation. We have written it in this kind of factorized form. So on the left-hand side, we have zero. And so our options are that for this equation to be satisfied, well, either this factor can be zero. So this is satisfied at time equals zero. Okay, so this has two solutions. Time equals zero, and that makes perfect sense, right? At time equals zero, I'm at this position. This is my displacement at time equals zero is zero. So that's one possible solution. The other possible solution then is that this factor is equal to zero. So this factor is equal to zero when we have t equal to 2v naught sine theta over g. That is the second solution. So this is basically the time that it takes for the particle to kind of complete its motion and land. So now that we know that, we can now look at the horizontal component and calculate how far the particle travels in this amount of time. So for the horizontal component, we know that the initial velocity, v naught, our velocity v is just given by v naught cosine theta, because again, going back to this diagram, v naught cosine theta is the component of the velocity along this x direction, and there is no acceleration acting in that direction. So that velocity is constant. If that's our velocity, well, the displacement is going to be given by the velocity times time. Okay, so we'll have v naught cosine theta times our time, which is there. It's 2 v naught sine theta over g. So if I rewrite this, I'm going to get 2 v naught squared cosine theta sine theta over g. That is the displacement, or to use the letter that we marked here, it's the range. And I can actually use a double angle formula. So sine theta times cosine theta times 2, that is actually equal to it's equal to v naught squared sine 2 theta. Okay, so that's just a double angle formula we've used there over g. And using that, we can then work out what angle gives us the maximum value of the range. So we know that this sine function takes values between plus and minus 1. So the largest value that this range can take is when sine 2 theta is equal to 1. And that's true when 2 theta is equal to pi over 2, or equivalently when theta is equal to pi over 4. And this is the result we quoted in the lecture. Basically what it means is that in order to maximize the range, what we want to do is launch our particle at exactly 45 degrees to the horizontal. And as I mentioned, that's because if I launch at too steep an angle, so if I launch up here, I'm going to get some trajectory which looks like that, so that's going to reduce my range. If I launch at too shallow an angle, I'm going to hit the ground before I have a chance to get very far. And kind of if we move from these two extremes towards the center, the kind of pinnacle, the longest range that we get is found when this launch angle is equal to 45 degrees. And this is how we prove it using this relationship.